Hey guys, so in this video I'll go over pages 108 to 111. The plan is to go over pages 108 to 109 in class, and if we have time in class to also go over 110 to 111. But if we run out of time in class, then you can find this video to help you out. This is also the same class video for Hudson. Hi Hudson. So in this question, and in each of these questions, there's going to be something that they're trying to test. And in this one, they're testing potential energy and the choice of zero. Does the choice of zero affect your interpretation of the system? Does it affect the results of whatever is happening? So let's see, in this question, an ideal spring of unstretched length L naught is 0.25, just as is seen here. And the spring constant K is 50 newtons per meter. Is hung vertically above a level floor as shown in the figure. The mass is 1 kilogram. It's attached to a spring when it's at its natural length. It's released and it's allowed to move freely. So I think the movement will be up and down. They're asking me to draw and label the forces exerted on each block in the diagram. And they want me to qualitatively consider relative magnitudes of the forces. The equilibrium point of the block spring system is shown as a dotted line. So this is the equilibrium position. Now, the block, just going back to this a little bit, the block is attached to the spring when it's at its natural length, right? So just at this position, it's not yet released. The only force that's acting is the force of gravity. The force of gravity. Because you might be asking, why isn't the force of the spring acting at this stage? Well, the spring is at its natural length. It has not yet been released, so there's nothing extending it, there's nothing causing tension in the spring, and therefore there is no restoring force in the spring, which restoring force would have accounted for the Stokes law. Remember, the force of the spring is equal to the spring constant times the displacement. So, however, in this case, when it's extended and it's at its equilibrium position, this means that at this position it's going to start going back up, right? Then at that point it still has the same force of gravity. So just make sure that these lines, these arrows are the same. And since at this equilibrium position it's momentarily at rest, it's going to accelerate upwards, yes, but it's momentarily at rest at that equilibrium position. And at that position, velocity is zero, so therefore the net force is zero. Therefore, the force upwards, which is the force of the spring, is also the same, and I hope this is clear. It's also the same length, which is the force of the spring, the same length as the force of gravity. So just label them force of gravity and force of the spring. Calculate how much the spring has stretched when the block is at equilibrium. Well, just remember in this equation, the force of the spring is equal to K times X. So I know force of the spring is equal to K times X, and that force of the spring, I hope you can see, since this is constant velocity and it's at equilibrium, since it's at equilibrium, that force of the spring is equal to the force of gravity. So I know force of spring is equal to force of gravity. Force of spring is given by K times X, which is X is change in displacement or its extension. Force of gravity is mass times gravity. So the K is 50, the displacement is what I'm looking for, delta X is equal to the mass is 1, and the gravity is, did they tell me what to use for gravity? I'm going to go ahead and use 10, because in most of these, yeah, I'm going to use 10 as gravity. They didn't tell me to use 10, so why am I using 10? You can use 9.8, but I just see that this will be a nice clean answer, so I don't want to pull out my calculator. So delta X, no, not divide by 10. Divide by 50 both sides. So I divide by 50 this side, divide by 50 this side, and I'll see delta X is equal to 10 out of 50, which is the same as 2 out of 10, which is 0.2 meters, right? You can use 9.8 and you'll find an answer that's very close to that. But to calculate the height of the equilibrium position of the spring with respect to the floor. So what's this height of the equilibrium position? Well, we know that up here is 0.25. We know that it's extended 0.2 meters, right? 0.2 meters. And if this whole thing is 1, then the equilibrium position is going to be 1 minus 0.25 plus 0.2. So that equilibrium position from the floor, so from the bottom up to this point, that equilibrium position is 0.45, so that means that will be 0.55 meters. So this is 0.55 meters. So there you have that. Angela is tasked with completing energy bar charts for the scenario described above and creates the chart below and left. This one, below and left. For the time just as the block is released. Okay. Complete the energy bar chart below and right. This one. That would depict the energy of the block Earth system as the block passes through equilibrium. So this shows us that just when it's released, all of the mechanical energy of this system is potential energy. And this is telling us that that potential energy is 7.5 joules. Let's first verify that. Just when it's released at this position, it has a height of 0.25, which is the same as 0.75 from the ground. I hope you can see that from the ground, that height is 0.75. And since the ground is my reference for calculating potential energy, its potential energy just when it's released will be mass times gravity times height. So the mass is 1, the gravity I'm using 10, and the height is 7.5. So I hope you can see that the potential energy is 7.5 joules, and that's what this graph shows, that it has a potential energy of 7.5. So that's just before it's released, its potential energy is 7.5 joules, and it doesn't have any other form of energy, so elastic potential energy is 0, and kinetic energy is also 0. But when it's passing through its equilibrium position, what's happening? So at equilibrium position, let's first check for potential energy. Since it's still a certain height above the ground, a height of 0.55 meters, it will have a potential energy, and that potential energy is this potential energy is mass times gravity times height, which is 1 times 10 times that height is 0.55. So that's a potential energy of 5.5 joules. So graphing that here on this thingy, on this graph, I have 5.5 joules as its potential energy at that position, right? So I have my box going up and down up to 5.5. Alright, we know that the total energy of the system, since this is 5.5, the total energy when passing through this equilibrium position, the total mechanical energy must equal the total initial mechanical energy. So far we have 5.5, right? But we know that all of this, the total of this side plus whatever we're going to add, the total must equal to 7.5. So far we are missing 2 joules of energy to be able to equal 7.5. Let's see where those joules are coming from. Since it's at an extended position in this final state, it's extended. That means you have elastic potential energy. Elastic potential energy happening due to an extension of 0.2 meters. So let me calculate that elastic potential energy. It's half times k times x squared, which will be half times k, which is 50, times x squared, which is 0.2 squared. Simplify, this is 25 times 4 over 100. If I square 0.2, it's 0.4, which is, it's 0.04, which is 4 over 100. And when I simplify this, 4 over 100 is the same as, 25 by 25, 1, by 25, 4, by 4, 1, by 4, 1, so my final answer is 1. So that tells me that the elastic potential energy is 1 joule, right? Elastic potential energy is 1 joule. Now, I must have made a funny assumption earlier that the velocity was 0 at that equilibrium position, but technically, I mean, the result shows us that it's passing through an equilibrium position, and since we have 5.5, add this one, that's 6.5, right? We need 1 more joule, and we know that since these are the only three forms of energy present, that joule is going to have to be kinetic energy, right? So it has kinetic energy at that position as well. So it has kinetic energy, it has potential energy, and it has elastic potential energy, which means that our mechanical energy has totaled to 7.5. So let me just go back to this and see if I drew this right. Since it has kinetic energy when passing through the equilibrium position, does that still mean that my velocity is 0? Yes, it's still 0, because equilibrium position means forces are equal, so my force diagram is correct. It does have energy because technically it's passing through it, right? It's passing through the equilibrium position. So yeah, I'm good. If you think I missed something, let me know. So going forward, Dominique, back to Dominique, says that the height above the ground does not matter. Only the change in height is relevant. She considers the equilibrium position to be 0 gravitational potential energy. Complete the energy bar charts for the block earth spring system when the block is initially released. So, according to Dominique, if we're only considering just the point where this thing is released, if we're considering its equilibrium position as our 0, right? So this is our 0 point. If this is 0, then we only have 0.45 meters up here, 45 meters up here, right? And since it started from this height, its displacement from this 0 position is only 0.2 meters. So according to Dominique, when it's just released, if we are using this as the reference, this line is the reference, is the 0, then its potential energy is only due to this height, which is the height of extension, which is 0.2 meters. So according to Dominique, the potential energy when it's released is just going to be mass times gravity times height. Mass is 1, gravity is 10, and the height at that position is 0.2. So the potential energy is just going to be 2 joules, right? According to Dominique, the potential energy is 2 joules. So that's the bar chart for 2 joules. And since when it's released, it doesn't have kinetic energy because it's not moving, it doesn't have elastic potential, so it's not moving. So the total energy of the system, just when it's released, according to Dominique, remember, is 2 joules. So that means the total energy when passing through equilibrium position must also be 2 joules. Now, Dominique helps us because we can see that when it's passing through equilibrium position, its height is 0 according to Dominique, because this is the 0 position. So since its height is 0, when passing through equilibrium, it will not have any potential energy. So potential energy will be 0. What else we see is that when it's passing through equilibrium, it's still being stretched a height of 0.2 meters. The stretch or the extension is still 0.2 meters, so we still expect it to have elastic potential energy. Elastic potential energy, which is half kx squared, which, since we're using the same calculation, 50 times 0.2 squared, will still give us 1 joule, right? So elastic potential energy is 1 joule. Boom, boom, boom. 1 joule. And since elastic potential energy is 1 joule, and the only other form of energy that's in this system is kinetic energy, and the total energy has to be 2 joules, then that tells us that the kinetic energy must also be 1 joule, right? 1 joule. So does this change anything? I don't think it does, because the motion of the system is still remaining the same. The energy transferred to kinetic and the energy transferred to elastic is still the same. So it doesn't matter where your 0 is, as long as your energy conversions are still followed correctly. Using the results of your bar chart to support, use the results of your bar charts to support Dominique's claim that the 0 point of gravitational potential energy does not affect the behavior of the block earth spring system. Reference specific details of the student's energy bar charts in your answer. Well, this is what I was talking about, that the choice of 0, and remember this is what this whole thing is about, the choice of 0. These 2 pages, that's what they are about. and for you to really understand this idea, that the choice of 0 does not affect the energy conversions in the system if the conversions are followed correctly or if the calculations are done if they're followed correctly. So we can see here that the choice of 0, right, does not affect the motion of the block, right? The motion isn't affected because it doesn't matter where the 0 is, the object still goes down when it's released and it still goes back up, like it will keep oscillating or bobbing. So the transfer of energy from elastic potential energy is still going to be the same as the transfer to kinetic potential energy. That's not affected by the choice of 0, right? Hope that makes sense. So what you can say here is that the motion of the object isn't affected. The same energy transferred happens from elastic potential energy to kinetic energy, irrespective of where the 0 point is, and the same amount of elastic potential energy, which is 1 joule, is transferred to kinetic energy, which is also 1 joule, right, irrespective of the choice of 0. So this result from the bar chart, and it still shows that the total mechanical energy of the system when it's passing through the equilibrium position is 2 joules, which is equal to the initial mechanical energy of the system, which was purely potential, which was also 2 joules. So referencing the bar chart, the total mechanical energy of this system when passing through equilibrium position is still equal to the total mechanical energy of the system at the point of its release, irrespective of the choice of 0. And this really is the point. Is the total mechanical energy the same? Yes. So Dominic is right that the choice of 0 does not affect the behavior of the block at spring system. Right? Hope that makes sense. Maybe something else I can add to this is that the kinetic and elastic potential energies are not affected. They're not due to the Earth block system. The kinetic energy of this object is not due to the kinetic energy of the system is not due to the Earth, like it's not due to the force of gravity from the Earth. Neither is the elastic potential energy. It's also not due to the force of gravity from the Earth, right? So those ones will still remain the same. They will still transfer the same. The transfer between those two will still be the same. So they are not affected by that. The only energy that's affected is potential energy, and that for the Earth spring system, the Earth block system only depends on the height that is your reference point. So I hope that's useful. So in case we run out of time in class, I'm also making a video for these 2 pages, 110 and 111. And in case we don't finish them in class, there will be a homework plus 112 to 113, of course. So an astronaut is lost in space near an alien planet and its orbiting moon, shown on right, not to scale. At a particular instant, the moon is directly opposite the astronaut on the far side of the planet, in line with the center of the planet, and at a distance r from the astronaut, right? So the distance between the guy and the moon is r. This one, they're trying to get you to understand gravitational potential energy, which is the title of that page. So I want you to mark an X on the diagram shown to indicate the location where the astronaut could move so that she would feel no net gravitational force. And just to give you an idea of this, when you guys were playing with magnets back in maybe 5th grade, right? If you put 2 magnets, even if it was north and south, at a certain distance apart, there was a sweet spot right here in the middle where you could put an object, or maybe somewhere here, or maybe somewhere here. There was a sweet spot where you could put an object. Sorry, this would have to be the same pole. So north and north, there was a sweet spot where you could put an object and it could not be attracted to either of the 2 magnets, right? At that position, we would say that the magnetic force, the magnetic attraction from either magnets is the same. So that means the net force on that little thing would be 0. So it's the same situation here that they're asking you to figure out. And you can try this magnet thing at home. You can put the magnet samples and see, try to find that sweet spot. So for this system, even for the Earth-Moon system or the Earth-Sun system, there is a sweet spot in between the two planets, in between these two planets, I mean the planet and the moon, where this astronaut would stand and would feel zero gravitational pull from either of the two objects, because at that point, the force of gravity on the astronaut due to the Earth, right, would be the same force of gravity on the astronaut due to the moon. Sorry, planet. Keep saying Earth. Planet would be the same force of gravity due to the moon. So where do you think that point is? Do you think it's closer to this side, or is it closer to this side? Take a second and pause and figure out the answer. So for sure, it's not in the middle, right? It's not in the middle. If the objects had the same mass, it would be in the middle, but they don't, so it's not in the middle because this one has a much bigger FG than this object has a smaller FG on the guy. So since this has a smaller FG, the astronaut would have to be standing closer to the moon to experience a zero net force and a zero pull of gravity. So I would put my X on this side of the half, on this side, right? Anywhere as long as it's clearly in this half would be fine. Okay, anywhere clearly in this half is fine. If you put your thing close to half, you lose the point. So we've marked our X. Now the next question is, if the planet was not between the astronaut and the moon, so no planet, right? Planet is not there, but the distance r was the same. Distance r is the same, planet is gone. Would the gravitational force on the astronaut by the moon increase, decrease, or stay the same? So remember, the force of gravity of the planet on the astronaut is equal to g, mass of planet, mass of astronaut, divided by r squared, d squared, where d is the distance between the planet and the astronaut. And the force of gravity on the astronaut by the moon is g, mass of moon, mass of astronaut, divided by r squared. So they're asking you, is this going to change when the planet is removed? Well, we can see that this has nothing to do with the planet. There is no mass of planet in this equation, right? So the force of gravity between the astronaut and the moon is not going to change. It's going to stay the same because according to this equation, it's not affected by the mass of the planet, so it stays the same. The astronaut's jetpack, this guy has a jetpack, is powered by an arc reactor. So this guy is like Elon Musk, next generation tech, that can supply near limitless energy to the suit's thrusters. The astronaut wishes to escape this planet-moon system to travel to other parts of this solar system, away from any other significant gravitational effects of other planets or moons. Consider the energy required to escape from the configuration shown above. If the astronaut was instead standing on the moon, would it require more, less, or the same amount of energy to escape the system? Well, if we look at it, if we look at this system, the moon, the Earth, and the astronaut, right, is somewhere here. This is the astronaut. They are saying that he's standing on the moon. So he's standing on the moon right here. If he wanted to escape, the gravitational effects of this moon, of this planet, and anything else in this solar system, would he require more, less, or the same amount of energy? Let's think about this. If he's going to escape, then the energy or the amount of work that's being done must be greater, right? Must be greater than. Well, let me not jump to the answer immediately. In order for him to escape the gravitational effects of this moon and this system, he would have to feel a force of gravity from the moon equals 0. He would have to feel a force of gravity from the Earth, right, equals 0, right? Now we know the force of gravity from the moon is equal to g, m of astronaut, m of moon, divided by r squared. In order for this force to be very, very, very small or insignificant or small enough for him to escape this gravitational pull, this R would either have to be very big, right? This R would have to be very, very big, because if this R is very, very big, then this force will be decreasing and decreasing and decreasing. For him to increase the distance between himself and the moon, guess what? Does he have to do the same amount of energy? No, because if he does the same amount of energy as the work done by the moon on him, he's not going to escape. He has to exert more energy, right? So let me explain this in an energy perspective. In an energy perspective, the energy done by his jetpack, right? The energy, that's all the work done by his jetpack, minus the work done by the Earth on the guy, right? So work done by the Earth on the guy, minus the work done by the moon on the guy, must all be zero, right? This, at least it must be equal to these two for him to escape their gravitational pull. So in order to get to a position where the work done by his jetpack is greater or at least equal to the sum of these two, then he has to exert more energy. I hope that explanation makes sense. If it doesn't, let me know. The astronaut is able to travel a very far distance x away from the planet moon system at a constant velocity, needing a total amount of energy E to do so. Explain why the jetpack must do work on the astronaut to maintain a constant velocity. So think about it this way. In order for him to be moving at a constant velocity, the net force on the guy must be zero, right? If the net force on him is zero, that means that because there's a force from the planet and there's also a force from the moon acting on the guy, right? These forces are constantly there because they're forces due to gravity. So for the net force to be zero, there has to be a force this way, and that force has to be provided by the jetpack. So because you have a force provided by the jetpack, and because you have distance being moved away from the planets, work done is equal to that force provided by the jetpack times the distance. So the jetpack must do work that is equal to the work done by the planet and the moon and the astronaut in order to maintain a constant velocity. So yeah, that's why it must do work for the net force to still be equal to zero. Sketch a graph of the force exerted by the jetpack to keep the astronaut at a constant velocity as she moves away from the planet-moon system. Identify the feature of the graph that could be used to determine the energy used by the jetpack to move the astronaut in this manner. Well, in order to think about, I think you can intuitively think about it and say, as distance is increasing, right? As the distance from these planets is increasing, does the jetpack require more force, or does the jetpack require less force? What do you think is happening? As he's getting further and further and further away from the planets, he's going to require less force because the force of gravity on him is decreasing. So your graph needs to have this kind of behavior, that as the distance is increasing, the force is decreasing, right? And as the force is increasing, the distance is decreasing. So intuitively, you can think of it like that, and then go ahead and draw a graph like this. Oh, sorry. The options are either a graph like this or a graph like this. So how do you decide between these two? Let's see. We know that the force exerted by the jetpack, right? The force exerted by the jetpack must be greater, must be increasing, bigger than the force exerted by the, sorry, it has to be equal. It has to be, for him to be moving at a constant velocity, the force exerted by the jetpack has to be equal to the force of gravity exerted by the Earth-Moon system. And the nature of this force of gravity is that it's G, M of that system, M of the astronaut divided by R squared. Now, all of these things are remaining the same. The only thing that's changing is this factor R squared. So the force that's exerted by the jetpack is going to be proportional to this term 1 out of R squared. And you know that a graph of 1 out of R squared looks more like the bottom curved shape. So that's how you can discard this one, this shape. That's how you can discard that and stick with the first one. All right. Identify the feature of the graph that could be used to determine the energy used by the jetpack to move the astronaut in this manner. What feature of the graph could be used to determine the energy used by the jetpack to move the astronaut in this manner? Still confused by this one? Hopefully I'll explain it in class. Describe the power required from the jetpack as the astronaut travels away from the planet moon system. Does he require more power as distance increases, same power regardless of distance, or less power as distance increases? I'm going to go with less power because we know that work done, right? We know power is the rate at which work is done. So work done divided by time. Work done is force times distance divided by time. I know that distance divided by time is velocity, right? So work done, power is force times velocity, and this velocity is the average velocity. Since this velocity is remaining constant, right, and the force is increasing, because we saw that the force is increasing, the force has to be increasing. The force required is decreasing. The force required as the distance increases is decreasing. So this force is decreasing, going down. Since this is remaining constant, this power also has to decrease. So yeah, that's what you have. Hope that helps. Bye.